Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Cadence with Megha Daga, who's going to talk today about convolutional neural networks. So, Megha, we've heard a lot about neural networks. There's a lot of buzz about them these days. Where does a convolutional neural network fit in versus some of the other types of neural networks?
So convolution neural networks are a kind of neural networks which have been designed specifically keeping image applications in mind, image and vision. They are to say where the objects are, what these objects are, and to classify them, scientists have found that convolution neural network fits the best thing in the category. There are other types of neural networks, for example, a recursive neural network. Now the distinguishing things about between these two are convolution neural network, CNN. CNNs are for image, like I just explained, but RNNs people have found have been very helpful in audio recognition because of the way our hearing mechanism is. So scientists are typically just trying to mimic how our neurons for different senses work and map them to different kinds of algorithms.
Part of this is our adaptation to the physical world, right? Really, what we're trying to do is get all these inputs from all these different sensors and process them in an intelligent way.
Exactly. That's exactly what they are.
So, where are you seeing this show up? What sorts of markets?
So CNN is everywhere right now where we are seeing a camera. Then we are seeing it in AR, VR. It's a big world about augmented reality these days. And all that depth recognition, putting objects in over there, they're all done through neural networks or moving towards neural networks if they were vision. We are seeing it in surveillance. Surveillance is another big thing about in the big cities and small cities where they want to track everywhere. Let's say an example of subway. We want to see who's getting into the train. Is the same person getting out of the train? Which station did he get out on? And those kind of things people are tracking using people detection and things like that, again, using neural networks. So, and last but not the least, automotive. These are the days where everybody wants to go towards that autonomous driving. And autonomous driving is, again, people are moving towards completely neural network based autonomous driving. They are still partial here and there, a mix of manual, mix of automation, but as they are going, people have come up with a way to make it completely automated and all neural networks. So it's everywhere to say.
Why don't you draw us out what a neural network looks like?
Okay, so let me show you how a typical convolution neural network looks like. As I said, they were derived based on how we perceive images, and what scientists have found that when an image comes in, it's processed in layers and layers, and that's how CNNs were designed. So let's say I see an image, and an image, I have an object in there. Now, this object will go through a bunch of layers. So it starts from, let's say this is my bounding box, and this is what I'm going to look at. So this frame, which we call ROI, region of interest in the image, it goes through a bunch of layers. So first it will start with convolution layer, which is, as the name states, one of the building blocks of this network. So there will be a bunch of convolution layers, and what it does is it is a filtering process, and there are tons of filters it applies to on this image. Each filter will basically give me different activation functions. So let's say one filter will tell me the edge of this object. Another filter will give me the color of this object. And all those things will get derived in, let's say, 3 filters. So 3 filters are telling me that. Once that is done, then it goes through another layer of a pooling. Pooling is basically a resampling layer. So these are huge data sets. So image data, like these days, are coming in 4K, 8K. So once we find the ROIs, even the ROIs are pretty huge. So for example, AlexNet, where a typical ROI is 224 by 224, we have that ROI. It's processed through several filters. The image, the data set is again expanded. So we need way to reduce this bandwidth. And one of the ways is pooling, which is a resample. So what it does is, let's say I bring a resample by a half. So it will resample the width and the spatial dimensions by half. Now again, these are all 3D data sets. So there is a depth also associated with it. This depth stays the same. It's only the spatial dimensions with the pooling is going to affect. And now it's basically the same thing, but just resampled by a fourth. So that will be pooling. There are several other stages which can be involved in between. For example, normalization like a ReLU, batch normalization for local normalization and stuff like that. Different networks are coming up with different strategies. And then these two kind of convolution pooling with something which will continue going. Like I said, it's layers, and these are the layers, 1 layer, 2 layer, 3 layer, 4 layer, and they are going deeper and deeper because they're finding more deeper you go, more accuracy you get. And at the end, there will be some kind of layer which will be an output classification kind of layer. Let's say it's a fully connected layer where it will have bunch of coefficients associated with each input node, and it will at the end just come up with, let's say, top 4 classifiers. One of them can be, let's say, Apple.
And these can become more efficient as you go forward too, right? So you can start teaching these devices to learn. You can start pruning some of the code out of this, and it becomes more efficient, and the neural network becomes basically learns as you go.
Yes, and so that's what's a CNN. You can see it as 2-part thing. One is a training and one is an inference. What I talked was a typical inference model. A training model is something which will happen offline, which typically takes days to months, and it is a recursive pattern where you keep feeding in tons and tons of data set, and it will keep adapting these filters which we were talking about, the coefficients of these filters, and tell you what is the best set of filters for that set of organization.
And do they go on consecutively? Are they concurrent? How do those two parts work, the inference as well as the training?
So training is something, once it's done, I mean, you can retrain a network. So a network can be trained for different things. For example, AlexNet, you can train it to detect objects. You can train it to detect people. Once you have done with the training, once you have the data set, you can just use that data set in the inference model forever. Once you have set, your object classifier, what kind of object you want to classify. So once that is set and once that is trained with the accuracy you want it for, you can just go ahead and do it.
And AlexNet is just one of several different reference designs, right, for convolutional neural networks?
Yes, it's one of the most talked about. It was a 2012 winner, and but it's it's not so old, but it's actually old in the world of CNN. There are many more which have come up after AlexNet.
So what sort of problems are we running into in developing these?
So let me talk about 3 more major problems which we are facing into CNN. First thing is the trends. As we all are seeing, these networks are evolving very, very rapidly. So first, let's just say the way these networks were. They used to be a very linear network, which means A comes after B, C comes after A, and so on and so forth. Now they have moved to something like branch networks, where they split and then they concatenate. There are third type which we are seeing, which are like gated networks. So as you can see, these are continuously evolving, and they will evolve because this is an area of research. Something is continuously developing every now and then. So we need a solution which is dynamic enough to face these challenges of trends. Then the second problem we are facing is of compute. So these are convolutions, right? These are filters. So there is tons of coefficients, there is tons of data, and they mean you have to multiply and accumulate them. So we need lot of MAC resources. And we have seen in over 4 years, the compute requirements have actually increased more than 16x. So where AlexNet used to be somewhere in 0.7 gigamax or so, we have come down to ResNets which start from 11 gigamax to 15 gigamax based on the flavor of ResNet. So it has gone 16x. and this is like 2012 to 2016. So we need a resource which can tackle these compute requirements as we are going forward.
How much of this gets done locally versus centrally?
So that's the thing where the industry is moving now. They want to do everything on device. And that's where the power comes into picture now. That once you want to do everything on device, you want it to be as efficient as possible, as low power as possible. Obviously, we can't afford, for example, let's say AR, VR, or wearable devices. Wearable devices, you need all these algorithms on your device, and let's say I'm wearing a watch which is tracking my motion continuously and calculating some kind of feedback based on that. Then if it becomes too hot, it's a burning hazard. So we need something which is very power efficient and still able to do so much compute on the chip.
And so basically, this is the way the human brain works, right? Because if you think about touch or vision, you're dealing with sensors that are doing some of the processing locally, because if everything came into your brain, it would overheat your brain.
Yes, and I guess our brain compute capability is way beyond these things, that we are still able to process tons of data, recognize several things in the image we are seeing without any issues, so forth. Yeah.
What's the goal here in terms of wattage? What are these supposed to run at?
So that's a very typical industry specific question. Different industry will quote different numbers. I can't specifically say, okay, these kind of industry will need certain watts of, but even like industry of automotive, which you can think in all these might be in the most upper higher side of the power, still talk about less than 10 watts or so on and so forth. So they want to stay there. That's their comfort zone. And they're crunching it further and further because these numbers are for the overall system. What you afford for this is way smaller than that.
And you have a massive amount of data which needs to be processed here, which leads to probably your next one, which is what, memory and throughput?
Yes, exactly. So that was compute, and then there is the bandwidth problem. Now, because we want to do everything on chip, and on chip with these DSPs, your local memory is so limited that you need to have a continuous flow of data from your system memory to your local memory. You want to minimize this local memory bandwidth issue. You also want to make it more efficient. So you want it in a way such that in a minimal, you can do a lot of reuse. And that is something you want from your bandwidth issue. So there are several things we can do in evolving DSPs where we can solve this bandwidth challenges of the traffic, basically the memory traffic.
Is part of the solution here really mining the data that you want? Do you need to pre-process some of this data to be able to move it forward?
There are several ways to go for the bandwidth reduction. So what you said was one of the ways, so basically pre-training it, right? So I can train my model in a way that it has, let's say, either a lot of sparsity into it, and by sparsity I mean a lot of zeros into it. So now I don't have to store the zeros. I will only store the data which has relevant data in it with a bit mask, and I will have an intelligent processor to understand that compression. Or I can train my network such that I squeeze it so much that my overall bandwidth itself reduces. For example, something like a squeeze net. It has made its network so deep and so squeezed that the memory requirement compared to AlexNet is several folds lower than what it is in AlexNet. So two different ways to approach in training your network itself. Other things, if you have sparsity, I already said for sparsity, we can have an intelligent DSP. So a DSP needs to be intelligent enough to use the compression decompression support on this so that it can utilize the bandwidth issue. We can also have a lot of software techniques to help in this regards. We can have something which we call as batching. So when we do batching, which basically means the reuse, what I talked about. So reuse of your coefficients. What it means, load several input data and one set of coefficients and deploy that one set of coefficients onto that several data. So now you're producing multiple outputs at the same time, but your bandwidth has gotten averaged out. So you won't be limited by your bandwidth. So those are different ways we can tackle the bandwidth issue.
And a CNN is something of a compromise too, right? Because if you go to a recurrent neural network, you're actually adding the dimension of time, so your data goes up that way.
Yes, so there are several other things with RNN. So with CNN, it's a feed forward. You don't have to think about the feedback process. Feedback process can add several other impacts. For example, one thing which I forgot to mention in bandwidth is these days people are highly advocating fixed point, right? So from float, people are moving to 8-bit, 16-bit. Now let's say 8-bit. 8-bit, the researchers have shown, industry has shown with 8-bit you can get almost the same accuracy as floating point, less than a % degradation. And with this, your memory bandwidth automatically reduced by 4x. Now, based on what you said about RNN versus CNN, if I'm working in 8-bit on RNN, that's a study we need to make because it's a feedback loop. In feedback loop, how the quantization works and everything, that needs to be studied further. Whereas in CNN, you are going in a feed forward way, so the quantization impact comparatively is probably minimal.
So if you're a hardware designer, what do you need to keep in mind? How does this differ from, say, an ASIC or an ASSP or some other chips that you've been developing?
Okay, so I will take this back to my first point where the trends came into picture. With a hardware design, like I said, I want something which is flexible. I want something which is future-proof because of the way this industry is evolving. And for that, I want something which is programmable. And that's where the DSP comes into picture. Anything which goes on the hardware, it gives me that rigid processing power, right? I cannot manipulate a lot of stuff. We have a lot of hardware out there which will do just the convolution on themselves, and everything else is getting settled on the other, whatever the host is, a DSP or a CPU or a GPU. But you are limited by the scope of that hardware, and we don't want that limitation out there. So we want something which is flexible. We also want something future-proof. So they are going in this trend. What about they come up with something else, in the next couple months? Or by the time your product releases, which is in next year or two, there might be something completely different. Then what do we do?
So is it one programmable device or is it multiple chips which may be heterogeneous?
It is a multiple. So that comes to another trend, which you just say a scalability. We want a solution which is easily scalable. We are moving, I started from mobile phones, but we are at automotives. Automotives needs several of these chips together. And because they need several of them together, we want a solution which can be easily scaled. We don't want a complex system. It should be easy to program, it should be easy to design. So yes, a good scalable solution.
So how quickly are these going to be rolled out, and where do you start seeing them? They're in some use today already, right?
Yes, and so we are already seeing them in the mobile application. We are seeing them slightly there in automotives and stuff, but they are moving very fast. There are automotives which are completely moving towards this all neural network based, so we are going towards that. Everything is going to be driven with this. People are creating these home based applications such that I'm in my car, obviously self-driven car, and there I can reach over the, through IoT and stuff, I can reach my home, I can see what's there in my refrigerator, and basically it's doing a lot of object detection using neural networks. It will tell me a count of what vegetables are there, how much are there, what can I cook, and what can they start with automatically. So by the time I reach, I already have a setup done for me. So it's going very fast and it's going everywhere.
One other piece which comes in on a lot of the IoT and connectivity type of applications is security. So it's fine for you to see what's in your refrigerator and what's going on in your house, but if other people can look at that too, you have a problem. How secure will these be?
So that's another field people are working intensively on, security. And they have already started looking into surveillance and automotives. These two are, you don't want somebody else to start controlling your car. So yes, there are big standards which people have to all start, which they are already following. I mean, if we look at ASIL-B, ASIL-C, ASIL-D standards, we will find all those predefined and what needs to be there from security point of view. So those things are there.
Megha Daga, thanks for a great explanation.
Thank you.